Can you hear me? Is this on? Doesn't sound like it's on, is it? It seems to be on my side.
Yeah.
All right, so I start with the second lecture on Feynman integral aspects. Just to remind you of where we ended up yesterday, is that we had a general parametric formula. And let me just do it in a very simple example. So let's look at a graph which has just two internal edges, two propagators, 1 and 2, external momentum p. And let me say that what the two graph polynomials are in this case. So we had a u polynomial and an f polynomial. So the u polynomial, remember, this could be computed by looking at spanning trees. So what are the spanning trees in the graph? Well, you can either take the edge 1 or you can take the edge 2. Both of them connect the two vertices. And if you take the edge 1, you're missing out the edge 2. And if you take the edge 2, you're missing out the edge 1. So the u polynomial is the sum of the two variables x1 and x2 that we got from the Schwinger trick. And for the f, you have to look at two forests. So instead of deleting one edge to get a tree, you have to delete another edge. And in this case, there's only two edges. So deleting both edges, and indeed then you cut the tree, the graph into two parts. The momentum p squared is running through it. So you just have this term from the two forests. And let me just say for simplicity that I put the two masses to 0. And then this is it. This is the entire f polynomial. Then I had something that I called the superficial degree of convergence, which was the sum of the indices, the powers of the denominators. So I would call these n1 plus n2 minus dimension over 2 times the number of loops. In this case, there's just one loop, so that's it. And then we had shown a general formula for the integral. So the integral I was the following. So in momentum space, it would have been the integral over d-dimensional Minkowski space of the loop momentum with this particular measure. And then we had two propagators in this case. So I would have, you can work out any momentum routing you like. This one. And n1 would be the power that I raised this propagator to. And then we also have another propagator, in this case, then 2. So this would be the general kind of integral you might want to look at in this case for this graph. And then the parametric formula for this one.
So, Eric?
Yes?
Will we have to run through the logic again with the forest?
Oh, yes, sorry.
Of course, I would have thought it's both parts, but I wouldn't have anything.
No, so indeed. So for the u, we took the tree. So we delete one edge, we get a tree. For the f, you have to delete one more edge because you want to get a forest with two trees. So here we have one tree connecting both vertices. Now if I delete one more edge, then the forest itself is empty. It doesn't have any edge. But this means it leaves two trees, which in this case are very simple trees, which don't have an edge, just the two external vertices. So this is my one tree, this is my other tree. Together they form the forest, and the two edges are not in the forest. Maybe it's a bit confusing. Maybe it's easier to look at another example like this one, which I explained last time. In this case, you can, for example, look at this forest, which has these two edges. Yeah. So I delete these three edges. These are deleted. And then I'm left with two trees, which have one branch each. Yeah. So a tree does not have to contain an edge, indeed. A tree can just be the trunk. I think it makes sense to use this terminology in this case. It's just, I think the safer thing to remember is take a tree and delete one more edge. Right? If I add an edge here, then I have a nice tree. If I delete any of these edges, I get a true forest. So I could also delete this edge. then I would have a forest which has a tree with 2 branches, and one of these stupid trees which is just a vertex. Okay. So maybe it's a bit degenerate, but it happens quite often that you have these kind of situations. So this is the momentum space formula. And then we had a parametric formula after doing the Schwinger trick and doing the momentum integral. And I gave several forms. I wanted to use the Lee-Pomeranski one for the purpose of this talk because it's maybe not as familiar. And for that, there was some prefactor of gamma functions, which is which you can work out. So this was a prefactor if you look up the formula from last time. Then there was also gamma factors from the measure in the Schwinger parameters, which I want to pull out here. And then we had an integral over the Schwinger parameters, which are always integrated from 0 to infinity. And the propagator exponents in the momentum space representation become the exponents of the Schwinger parameters in this representation. So this was the Schwinger parameter integration measure, and then the thing we had to integrate was u plus f to the minus d over 2. So in this case, it's just x1 plus x2 minus p squared x1, x2 to the minus d over 2. Okay. So this would be the Lee-Pomeranski way of writing this one-loop integral. And for the purpose of this talk, I mean, I'm aware that every one of you has probably computed this one-loop integral. You can write this thing in terms of gamma functions as well. It's this 2-loop master integral. But the point is you don't want to do that, because in general, you can never do this. In general, if you look at a Feynman integral, you have this parametric representation. And maybe in some very special cases, you can write it as some hypergeometric functions, PFQs or whatever. But in general, you will not be able to do more with it. So the point of this talk is to figure out how you can, just looking at this polynomial, derive all the properties you want about the integral that you otherwise can't understand in a more explicit way. So which is why I want to stick with this formula. And if you want to check in an exercise how these things go, you can always replace this by their gamma functions and check that the statements that I make are actually correct by reading it off. So this is the kind of thing we want to look at. And now the questions for this talk are, well, we have derived these formulae in a very symbolic sense. So there are several questions. So the first question, when does I converge? So when do these integrals make any sense? The second question is, what is the analytic continuation? Because as you know, the main idea behind dimensional regularization or more general analytic regularization is to take this formula. And the beautiful thing about this formula is that the dimension is just an exponent here. And also these propagator powers, they only are some exponents. So if you take this integral here, it makes perfect sense to put in arbitrary values for d. You can put any fractional values, whatever. You could put d equal to pi or things like that. Doesn't matter, right? So this expression is always a two-dimensional integral and gives you something that, at least on a symbolic level, would correspond to a momentum space integral over an arbitrary d-dimensional space. So I want to talk about dim-reg and so on, this parametric representation, where it's just a question of asking when does this integral converge for which values of d. Right? So it's clear that this integral, if it does converge, it gives you an analytic function of d. Because a convergent integral, the integrand is an analytic function of d, so the integral itself will be analytic. This is standard calculus argument. But then the question is, well, this only converges in some region. But we want to evaluate it. If you do dim-reg, you want to go to the poles or even more singular regions. So you have to understand somehow what is the structure of the analytic continuation of this function. And in general, analytic continuation is a very subtle thing. So recall, for example, if you take a function like the logarithm, log of z, this is nice holomorphic function. If you restrict it to some simply connected domain, so So for example, if you look at the region where the real part is bigger than 0, so you only look at the right half of the complex plane, and this is an isomorphic function, but now you want to study its analytic continuation, then you figure out suddenly it becomes multi-valued. You get a monodromy, you get 2 pi i's. So it does not make sense to talk about the value of log of z on the other side without also specifying how you got there, along which path you did your analytic continuation. So in order to get well-defined values for Dirac, that's not what you want. If we had monodromy, we would be dead. So the whole point is to show that if you have a meromorphic function, for example, the gamma function, then we have no monodromies. So the point is that we're always using in Dirac calculations that these integrals, even though they're only convergent in a very small domain, that they actually extend to meromorphic functions which are well defined, and then we use these expressions to define counter terms in minimal subtraction and so on. So I just want to briefly remind you of how this goes in the case that you're all familiar with, which is the gamma function, right? Because we also have this prefactor here, and I've treated it as though we understood everything about it, so let me just briefly recall how this goes. That's the wrong one. So what was the gamma function? So you can define it in this way. The integral from 0 to infinity, x to the n minus 1, e to the minus x dx. But already yesterday we had some question because the problem with this formula is that it only makes sense for a real part of n greater than 0. Otherwise, this integral is divergent, it doesn't make any sense. So the answer to question 1 is clear. When does this converge for real part of n greater than 0? I mean, that's very easy to see from the formula. If the real part of n is smaller, you get a divergence at 0. At infinity, you never have a problem because the exponential kills everything. So how do we understand? So we have defined an analytic function gamma of n on the right half of the complex plane. How do we get into the left part of the complex plane? But this is integration by parts. So how does this go? Well, you take this integral, and now we just integrate by parts with these two factors in the integrand. So we integrate this one. So then we get x to the n over n, e to the minus x, from 0 to infinity, and then minus the integral where we hit e to the minus x to the derivative. Of course, then this just becomes a plus, and we have e to the minus x again. And here at the upper boundary, this is always 0. At the lower boundary, well, at least if you're in this region where real part of n is bigger than 0, then this x to the n also goes to 0. So this goes to 0. And this here is nothing but 1 over n times gamma of n plus 1. So this is the IBP relation, which gives you the functional equation for gamma. But what is the important point of this functional equation? Well, it gives you an explicit way to compute the analytic continuation, which otherwise could have been more complicated. So if we repeat this, we can repeat this an arbitrary number of times. So we can also write this as 1 over n, and then n plus 1, and so on, n plus k. Then we would have the integral 0 to infinity x to the n k to the minus x dx. And the point is that this integral here, this converges and is holomorphic in the region where the real part of n is greater than minus k minus 1. Right, so we have an infinite number of integral representations for the gamma function because we can choose any value of k and get a different integral that gives us the gamma function. But the point is the higher we choose k, the bigger is the domain of convergence of the integral. So with the higher we make k, the further to the left of the imaginary axis the convergence domain extends. So using this formula we can... Yes?
So we just question. You said it's 0 here for the region of convergence in the AVP?
Yes.
And what happens there if it doesn't get the region of convergence?
So this formula only makes sense for real part of n bigger than 0. Otherwise, this term doesn't make sense. But remember that initially we only had defined a function on the right of the imaginary axis. So it does only make sense to talk about that. So this identity here, first of all, is an identity when the real part of n is greater than 0. Yeah? Because you only talk about a function we have defined on that part. But now we're saying that in this domain, we have this identity. And now the right-hand side of this identity is an analytic function in a bigger domain. So we have an analytic function which is defined here. So this is where gamma of n by the original integral is defined. And now we have our strip here is minus k minus 1. And now the right-hand side of this equation is a function that is holomorphic in this domain, in this bigger domain. But the point is that these two domains overlap, and in this overlap they coincide. And now we have uniqueness of analytic continuation. If you have two analytic functions which are equal somewhere, then they are equal everywhere. Because you can get them from analytic continuation from the region where they coincide. And analytic continuation is unique along a path. So this is the trick we use, right? So we derive a different integral equation which coincides, which gives us the same value in the original domain of definition, but which also happens to have a larger domain of definition. And then we know that the right-hand side gives us an explicit convergent formula for the analytic continuation of the left-hand side. I mean, this may seem very pedantic to you, but it's a very important concept of what we're doing here. That we're giving a convergent integral formula for the analytic continuation of a function into a domain where our original integral definition was ill-defined. Yeah? And this is what you're doing with Feynman integrals in limerick all the time. You're always evaluating them, or most of the time you're evaluating them at a point where the original integral expression actually doesn't make any sense. But what this shows you is that this is not a problem because there's a unique, well-defined way how to get there. This defines you the function in some domain, and then with integration by parts identities, you could, if you wanted to, derive integral expressions, integrands, which are convergent in the domain where you want to evaluate it. And the second feature you see from this formula is that you get these explicit poles here. Yeah, so this thing here, this integral is holomorphic in the region. And so all the poles come from the integration by parts denominators that you introduce. So you can read off exactly that the gamma function has simple poles precisely on 0, minus 1, minus 2, minus 3. And the whole message is that the exact same qualitative picture goes through for any Feynman integral. And that's what Limerick is. I just wanted to maybe make one more comment here, because that featured yesterday. So when you think about the Schwinger trick, so what was the Schwinger trick? We used this formula, d to the n is 1 over gamma n integral right, this is what we did. And we already had the problem. Well, we had two problems. One problem was that d better be greater than 0, which we could organize with the Wick rotation. The slightly more constraining problem was that we also wanted n to be greater than 0, or actually real part of n greater than 0 is enough. So what happens if you want to use this formula for an ISP, for a numerator, right? So if we wanted to put n negative, then we have a problem because this integral does not converge for n negative. But we can use the same trick, right? We can do an integration by parts. So let's do an integration by parts. This integral converges in this region. Let's stay in this region where this integral converges, still for positive n, but derive a different integral representation, a different Schwinger Trick formula. So we did exactly the same. We do exactly the same thing as we did before. So this becomes an xn to the n. And remember, then we have to have minus d by dx of the other factor, right? This is just the integration by parts rule applied. And there is a reason why I don't carry out this derivative. Yeah, I mean, you could carry it out, you pull out the d, but let me leave it like that, yeah? So what we get is, well, we can use the functional equation of gamma to absorb the n into the gamma n. So I can also write this as 1 over gamma n plus 1 integral 0 infinity x to the n. And then we have one derivative, minus d by dx e to the minus xd dx. Does this make sense? And again, of course, you can repeat this any number of times. So what you end up is you get n plus k. If you do this k times, and you have the integral x to the n minus 1 plus k. And then you have k derivatives right? And all of these formulae converge for a real part of n bigger than 0. But the point is, of course, the higher you make k, the larger the region of convergence this becomes. Right? If you put k to 10, then the whole formula converges for all real parts of n greater than minus 11. So if you have a 10th power of a propagator in the numerator, you just apply this formula often enough, and then you get a convergent integral representation like this. And in this way, you can extend this representation here to arbitrary values of the n, right? So a priori, just in deriving this formula and using this Schwinger trick, we have assumed that the real parts of the n are bigger than 0. Now I'm telling you that these integration measures there, you can replace them by any of these other formulae, and you will still get a valid integral representation. Yeah, so there's infinitely many parametric integral representations for the same integral just because of integration by parts. And if you have a negative index one, you can use this formula. And actually, there's a great simplification which takes place. So suppose n is a non-negative integer, a non-positive integer. Suppose n is 0 or minus 1 or minus 2. Yeah. So either we have a numerator to some power or nothing at all. Well, then let's choose k to be 1 minus n. Right? So this is now a positive integer. So we apply k integration by parts with this formulae. And what happens then? Well, by construction, it means that this power of x goes away. What happens to the gamma function? This becomes gamma of 1, which is 1. So this goes away, this goes away. And we only have to integrate a couple of derivatives, right? So this means that this integration x to the n minus 1 dx over gamma n, we replace this by the equivalent formula, where we now just have the integral. And we are allowed to do that, that's the point, right? Where we have dx, and then we have minus d by dx 1 minus n times of whatever, right? I mean, you should always think the following, that I kept this derivative here because I wanted to leave the exponential so that afterwards we can do the Gaussian integration. So the point is, if you do it this way, you can keep doing the Gaussian integration, just afterwards you have to hit it with the derivative. So on the right-hand side somewhere, right, we have our u plus f to the minus d over 2. So, and this is what this derivative is acting on. Yeah? And of course, you take the integral of a derivative, so you can replace you can get rid of the integration. You just do one derivative less, evaluate infinity and 0. And now you assume that by infinity, because there will be some dependence on x in here, this thing will vanish for positive d. So you only get a contribution from the lower boundary where x is 0. So this whole thing, again, gets just replaced by, you take minus d by dx minus n times, and then you evaluate at x equals 0. Yeah, so the bottom line is if you have a numerator and you want to treat it as a fake denominator, you can do this with the same formalism. So you have a new Schwinger parameter for this numerator that you treat it as a denominator. But now this integration again disappears actually and just becomes a couple of derivatives. Yeah. So this is what I mentioned. This goes back to Tarasov. So this whole idea of tensor reduction to scalars in the parametric representation. So anything in the numerator can be constructed by acting with some derivatives on some auxiliary variables that you then set to 0. Yeah. Any questions on this? Okay. So now you understand how to make sense of this for arbitrary values of the n in principle. Well, it's still not true. We only discussed the Schwinger trick. But of course, there's a non-trivial question whether this integral converges, because there's also this polynomial here that plays a role. So can we understand when this integral converges? Now, and for this type of integral, this is always a question about power counting, which you all know. So let's try to figure out when this integral converges. Well, I've deleted the integral. So we had some integral over dx1 here, and we had some integral over dx2. And let me just write there's an x2 to the n2 minus 1 here. So for the moment, let's just look at this subintegral, right? So for a fixed value of x1, there's this integral over x2. You have this kind of expression. So what do you normally do? You look at what happens at the boundaries of the integration domain, right? Because if p squared is negative, right, and this is positive, so there's the integrand is smooth in the interior, so the only sources of divergences can be at the boundaries. And if the dimension is big enough, so we have to look at small x2 and large x2. This is where divergences can come from, right? So for the convergence, consider small x2. Well, what happens to the integrand? Well, the integrand in this limit, when x2 becomes very small, is x to the n2 minus 1 dx2. And then this stuff, I mean, if x2 gets small, we can just replace x2 by 0 here. So this is just x1 to the minus d over 2. Well, but for the integral over x2, this thing doesn't contribute, right? So it's really only this thing that matters here. And we want to see what happens for a very small x, and then you see that this n2 has to be bigger or equal to, bigger than 0. Otherwise, you get a logarithmic or even worse divergence at 0, right? So we certainly need n2 to be bigger than 0. Otherwise, we get a divergence at x2 very small. And by symmetry, the same goes for n1. So this is the condition you get from this boundary. Then you can do a similar analysis at the upper boundary for the x2 integration. So what happens there? So by the symbol, I mean I don't really care to integrate from 0 just from somewhere very large to infinity. I want to study what happens at infinity. Well, of course, we still have the x2 to the n2 minus 1 dx2. This is always there. But now when x2 gets large, we cannot completely neglect this factor here, because then also for large x2, right, we can neglect the x1 term. And this thing becomes x2 times 1 minus p squared x1 to the minus d over 2, right? So again, for the x2 integral, this thing is just a spectator, so we only look at this. So we have something like x2 to the n2 minus d over 2 minus dx2 over x2. And for this, in order for this to converge, if you wouldn't have this term, this would be logarithmically divergent at infinity. So this has to fall off somehow. So you want n2 minus d over 2 to be negative. Right? So from here we get another necessary condition for convergence, which is that n2 is smaller than d over 2. Right? If n2 gets bigger, the thing blows up at infinity. And again, by symmetry, you get the same condition for n1. So we have these two conditions, which I hope you agree are obviously necessary for convergence. So the question is, are we done, or is there something else to check? Any conjectures, suggestions?
X1 and X2 both being small.
So you should look at both being small. That's a good idea. Because so far we only looked at, we always kept one variable frozen and just assumed we can look at the other. But there may be extra divergences which come from other regions in integration space. So let's look at this one. Yes, please.
So the p is now in the Euclidean.
Yes.
And when you say p squared can be negative, then this means it's all minus?
Yeah. My lecture is all minus.
Okay.
I think most lectures here are all minus. I think. So we look at both being small. So let's say x1 goes to rho x1 and x2 goes to rho x2. And we want to look at what happens with the integrand when we rescale the variables and we send rho to 0. So we're zooming into the region of integration domain where both x1 and x2 are very small, and they get small with the same kind of speed, so to say. What happens? Well, we have the integral. The integrand is we have this x1 n1 minus 1 dx1. You have the x2 n2 minus 1 dx2. So now this gives us a factor rho of n1 under this rescaling. Here we get a factor rho to the n2 from this measure. And then we had the polynomial x1 plus x2 minus p squared x1 x2. Now this gets a factor of rho. This gets a factor of rho. This gets a factor of rho squared. But then for very small rho, this is vanishingly small compared to the terms with rho, right? So for very small rho, this just becomes rho times x1 plus x2. So for very small rho, the integrand just becomes this thing to the minus d over 2. Minus d over 2, x1 plus x2 minus d over 2. So this contribution from this sector of the integration space, of the integration domain, scales like rho to the n1 plus n2 minus d over 2. And for this thing to be convergent, if you zoom into an arbitrarily small region of integration space, the integral contribution from there has to vanish. Otherwise, we have a divergence. So if we want to send rho to 0 and this thing should vanish, we have to have the exponent to be positive. Right, so we get a necessary condition that we need to have fulfilled for convergence, which is that this thing better be positive. Right, so this is just power counting in this particular sector. This doesn't work. I hope that's clear. But now are we done, or do we still have to check something else? Is this a never-ending game? We could send rho to infinity. What about other things? Maybe we could do something weird. Maybe we could do x1 goes to rho squared x1, and x2 goes to rho of x2, rho times x2, right? So this would mean that we send x1 to 0 much faster than x2. And depending on which, I mean, here it doesn't matter, but if you have a general polynomial, you can imagine that if you do different scalings, suddenly a different monomial might be the dominant one, and you get a different power counting. So in general, you have infinitely many things to check, right? For any scaling, whatever exponents you choose, you get a necessary condition for convergence. So we have two problems here. One problem is how do we check infinitely many conditions? And the second question is, are they even independent? And already here you see some redundancy, because we've derived three conditions, right? We have derived that they should be less than d over 2, they should be positive, their sum should be at least d over 2, but already you see that 2, sorry, you can't read this, so 2 and 3, okay, I read it right, so 2 and 3 imply 1. Right? Because 3 says that n1 is bigger than d over 2 minus n2, and by 2, this is bigger than 0. Yeah, so actually this condition, we can forget about condition 1. If you check condition 2 and condition 3, we're already implied condition 1. So if you do this in a very naive way, there's two problems. First of all, you're never really sure if you have checked everything you need to check. And the second problem is that there may be redundancies among the conditions you derive. So how can we do this in a cleverer way? So in general, rescaling, or how do I call it? General power counting. So we send xa to xa times rho to some power, lambda a. And these lambdas are real numbers. We chose integers, but you could choose any weird scalings if you wanted to. You don't have to, but in general you could. And this means that the integrand, if you do this rescaling, then our integrand of our formula will go like some power of rho, and I denote this power by rho of lambda, omega of lambda. Yeah? Times something plus higher orders. I hope you can read this. Can you read this? It's small. So I mean, the integrand will scale to some power with some power of rho. This power is denoted omega. And it depends on how I rescale, times something which to leading order is a constant independent of rho, plus things which vanish when rho is small. So to leading order, there's a certain power law behavior of the integrand, which you can encode like that. And then the obvious statement is that it is necessary that all of these scaling degrees, all of these omegas are positive. If any of these omegas is 0 or negative, you can immediately prove that the integral has to be divergent just by looking at the contribution from this particular region of the integration domain. If you think a little bit longer, you can convince yourself and prove that it's also sufficient. So if in every corner of the integration domain you have this power counting positive, then you can actually bound the integral very concretely by something finite, and you can show the convergence. So this is the first observation. Maybe just to make clear how this relates to what we did. So this omega, if I choose this as my lambda vector, so this means I scale, so this is lambda 1, the exponent of rho in x1, this is lambda 2. So this means exactly the scaling there. So I scale x1 by rho, and I do nothing to x2. x2 is not touched. So I keep x2 fixed and only send x1 to 0. So this is the first thing we did. All right, so here if you do the power counting, you get exactly n1. If you do the thing with 0, 1, you scale the other one, you get the power counting n2. Right, and the requirement is that they should all be positive. Now we also did send things to infinity, which is the same as scaling them by 1 over rho and sending rho to 0. So these other conditions, so this here is minus n1 plus d over 2. Yeah, so the first line here, these are the conditions 1, that these are positive. The positivities of these are the conditions 2. And then we had this uniform scaling where we scale both with the same power of rho. And this was 3. But you could do anything, right? You could look at other scalings. So how do we know that these are all we need? So maybe the lemma to note here is that this is a very general statement. If you have polynomials, if you take m polynomials, with positive coefficients, so Euclidean in the Feynman integral case. I mean, you can weaken this a little bit, but not too much. Then you can look at an integral of the form, you integrate, you can't read this. Then the integral over your variables from 0 to infinity of the product of these polynomials, can't read this, right? To some powers. So this is a class of integrals that is just a generalization, right? So in the Lie-Pomeranski, we just have one polynomial to the d over 2. We had another representation where we had u and f separate with certain exponents. But this is a very general statement here. So you can look at arbitrary integrals of this type, take a bunch of polynomials, raise them to some powers. You want to integrate them. Then this integral converges if and only if this omega is bigger than 0 for all scalings, except, of course, the trivial one. Right? I mean, if you don't scale anything, then the integrand will not depend on rho, so it will be rho to the 0. So omega of 0 will be 0. But any non-trivial scaling, if you go in some corner, the integrand has to vanish. So as I said, this is a simple thing, check. The non-trivial thing is how do you figure out what this omega lambda is? Well, in the examples, I think it's been clear what happened, right? So what is omega lambda in general? Well, we had our polynomial x1 plus x2 minus p squared x1 x2. And under the rescaling, this becomes rho to the lambda 1 x1 plus rho to the lambda 2 x2 minus p squared rho to the lambda 1 plus lambda 2 x1 x2. This is just what happens for an arbitrary scaling. So sorry, this is P, and this is rho. And then what matters is the leading degree, so the smallest power of rho. All the higher powers of rho will be vanishingly small in the limit when rho goes to 0. So we look at the smallest power of rho that we have here. This gives us a contribution to the scaling degree from this part of the integrand. We also have this part of the integrand, which is trivial to compute, right? So we conclude that the scaling degree, what is it? Well, we have these terms, x1 to the n1 minus 1 dx1. If you do the scaling, well, just every x1 becomes a rho to the lambda 1. So we get a rho to the lambda 1 times n1 from the x2 integration measure. You get a lambda 2 times n2. And then from the Lie-Pomeranski polynomial, you get, as we just computed, you get rho. But first of all, you have this minus d over 2 that you raise the whole thing to. But then what is the exponent of rho inside? Well, it really depends, right? It's the minimum of lambda 1, lambda 2, and lambda 1 plus lambda 2. Yeah. So there's some constant here, and then we have stuff which vanishes for small rho. Does this make sense? I mean, I'm trying to be very. This should be simple, yeah. So if you think this is way too simple, then that's good. It should appear simple. Sorry, this is not omega, right? What I've written here is how the integrand behaves. This is how the integrand scales, and omega was defined to be the exponent of how the integrand scales. Okay. So this omega is this here lambda 1 n1 plus lambda 2 n2. And let me write this as the scalar product of lambda with n. Yeah. This is from the measure. These are these two terms. And then we have this term with the minimum. Then we have minus d over 2 times the minimum. And let me also rewrite this. So why do we have lambda 1 here? Well, we have lambda 1 because this monomial x1 has exponent 1 and there's no x2. So I could also write this lambda 1 as lambda dot 1, 0. It will make sense why to write this in a second. Yeah. Now the lambda 2 I could also write as lambda dot 0, 1. And the lambda 1 plus lambda 2, well, that's just lambda dot 1, 1. Okay. So what this says is that the condition to be convergent is equivalent to the statement that for every lambda, for every non-zero vector, we want the dot product of lambda with our indices n to be bigger. Yeah, this whole thing should be bigger than 0, to be bigger than d over 2 times the minimum of the dot product with these through vectors. Okay. So now we can draw a picture of this. Let me draw a picture. So we have lambda 1, lambda 2. Here is 0. Let's say this is 1. And then we have 3 special points here. We have the point 1, 0, we have the point 0, 1, we have the point 1, 1. And these are just the exponent vectors of the monomials in the polynomial. Right? So we have x1, x2, and x1 times x2, which are the 3 monomials in the u plus f. And these are just the exponents of the x's in these 3 monomials. So these 3 points we read off from u and f. And now this condition says that we want that our so omega lambda greater than 0 is equivalent to the fact that lambda dot n is bigger than d over 2 times lambda dot these three special points. So now let's look at the following. Let's look at the triangle we have here. So we have a triangle that is the convex hull of these 3 points. Now let's suppose we take a point which is outside. Let's suppose our n is here, that n over d over 2. So let's normalize n by d over 2. So just think in 2 dimensions over there for the moment. So suppose our point n is here, then we are divergent because, for example, let's look at this direction, at such a direction, lambda. Yeah, so let's take this vector lambda and scale the variables in this fashion, according to this vector. Then the problem is when you go along this direction, then you hit this point that I just drew. You hit it first. You hit it before you hit any of the monomials in the polynomial. Yeah. So that means that the dot product of n with lambda is smaller than the dot product of lambda with any of the 3 points, because it's closer to the origin, right? So it will violate this condition, right? Because for this point of n, there is all the other points will have a bigger dot product, but you want that the dot product with n after normalizing by d over 2 is bigger than any of the 3 vertices. So this is a divergence. And similar, no matter whenever you put this point outside the triangle, you can always find a direction. Like when you point this point, take this direction, take this vector lambda, take this direction. Then you will hit this point before you hit any of the vertices. So again, this condition will be violated. Now, if you're inside, then you're fine. Right? If your point is inside, then no matter from which direction you come, you first hit one of the corners by definition of the convex hull. Yeah. So the upshot is that the domain of convergence is precisely the interior of this triangle. Okay. So from this very simple rewriting of what convergence is, you get 2 nice conclusions, which are very important and which you have used all the time, maybe without being aware of it. So, corollary. So the first corollary is that this integral, now in my notation I just want to stress that we really are worried in this lecture with the dependence on n and the dimension. Now we talk about the kinematic dependence another time. Today I'm just studying the dependence on the regulators, on the dimension in particular, but it doesn't pay any extra cost to do it for all n, not just the dimension alone. So this thing converges this precisely when n is inside d over 2 times the interior of this triangle. Okay. And in general, what is this triangle? More generally, remember how we constructed this. This was just the convex hull of all of the monomials which appeared in the polynomial. So consider your polynomial that you have u plus f, which is some sum of monomials, right? So it will be the summing over some vectors v. You have some coefficient, and then you have x1 to the v1 times xn to the vn. And most of these c's will be 0, and then a couple of them are non-zero. And then you just take the polytope then you replace the triangle by whatever is the polytope, which is called the Newton polytope, which is the convex hull of all of these vectors v such that CV is non-zero. So you read off the exponents of the monomials in U plus F, take the convex hull, you get a polytope. So this is called the Newton polytope. And then you look at the interior of this, the internal points, so you cut off the boundaries, and then you can read off the domain of convergence.
Erik,
Yes?
are we guaranteed that the CVs are all positive?
Well, this is now an assumption. So if your thing has a Euclidean region, then yes. Right? I mean, you can slightly weaken this as long as the parametric interrepresentation only has divergences from the boundaries. Then the analysis goes through. But what can go wrong is that if you're in Minkowski, you can get divergences from the bulk somewhere. And this is obviously not regulated by these ends, because the ends sit only on the boundary. And then you have to do more. Then this formalism doesn't work. If you're really nasty, you can cook up things where you have to introduce extra regulators which go beyond Dimreg and other ones. So for the most generic polynomial, you need more construction. So this is nice and beautiful, and it always works when the divergences come only from the boundaries of the integration, which is what is normally associated with the UV and infrared divergences. So everything which has a Euclidean region, this is fine. And as I said, in many cases it works also beyond that, but you have to be careful when you go beyond. But I'm not aware of any general theory in this totally general case. So I wouldn't even know what to do. Okay, so the first observation is that we have this very geometric interpretation of what the convergence region is. The second corollary is, well, we learn that the thing does actually converge somewhere, right? So if the dimension of the polytope is the full, if it has a full dimension, like in this case we were in 2 dimensions, we had 2 variables, and we had a triangle. The triangle is 2-dimensional. That's good. Then it has an interior. So the interior is non-empty, so there are points where it converges. Convergence domain is non-empty. So whenever you have a Feynman integral, you look at U plus F, and as long as you can really construct a full-dimensional polytope from these monomials which appear, then there exists at least some region in dimension and n space where this integral converges. If this doesn't work, so if the thing is of codimension, then you always say there's a vacuum subintegral or a scaleless integral, then there's no way to define it other than to define it to be 0. I'm sure you've come across this in Dimreg calculations, but this is the geometric explanation why it has to be. Right, so what could have happened, suppose our polynomial would have been just x1 plus x2. Right, then we would only have had these 2 points, and the convex hull, the Newton polytope, would only be this line. But this is 1-dimensional, and then we can't have a proper interior, and we don't have convergence. If you're somewhere on this line, if you come from this direction, we can also scale from the other direction, and they can't be both positive. They're both the same at this point. But don't worry too much about that. And the third corollary is we only have to check finitely many constraints. Namely, we only have to check omega of lambda is 0 for all facet normals of the Newton polytope. So what does this mean? In order to be finite, to be convergent, we have to check that omega is positive everywhere, we have explained that this is equivalent to saying that we are in the interior of the polytope. And how do you check if you're in the interior of a triangle? So let's go back to the original setup. How do you check whether you're inside this triangle? Well, you only have to check three things. You have to check that you're to the left of this line. You have to check that you're below this line. And you have to check that you're on this side of the diagonal. Hope you can see this. Yeah? So you only look at the boundary components of your polytope, and then you only have to check one condition for each boundary component, and then you're guaranteed you're inside. And you're also guaranteed that these conditions are all inequivalent. Because if you forget a boundary, then you're also allowing points which sit beside that hyperplane, which you don't want. Okay. So you see there's three things we have to check, and these are exactly the three conditions we had, right? This was the condition that n1 plus n2 minus d over 2 is bigger than 0. This is this condition here. This is the line where we asked that n1, n2 is smaller than d over 2. And this is the line here where n1 is smaller than d over 2. So we see from this picture that these initial two constraints, so we had these initial two constraints where n1 was bigger than 0 and n2 was bigger than 0. And they're true. I mean, the triangle is contained in the region where, in the positive orthant, in the first quadrant. But we don't have to check these. It's already implied if we only check that we're on these three constraints. Okay. So that took a little bit longer than I wanted, but I can, yeah, that's a good point for a break, actually. Let's do a 5-minute break.